Dating back in the 1600s, it is a common knowledge that the simple falling of an apple from a tree spark-plugged a universal law that changes the narrative about how matter behaves in motion, which led into the introduction to gravity, discovered by a mathematician and physicist named Sir Isaac Newton. Since then, his published book Philosophiae Naturalis Principia Mathematica, or Principia in short, was one of the crucial foundations into the development of the study of physics.
Based on the definition about physics, this is a branch of science that is concerned with the interaction with the nature and properties of matter and energy. One of the major topics included in the study of physics is about the concept of energy and momentum. In today's video, we are all going to discuss this, as well as a physics laboratory experiment to prove the definition of the impulse-momentum equation.
Hello to each and everyone. My name is Charles Gabriel M. Mijares,
And my name is Miss Jamie Ann Capili,
and we are your guest speakers for today. And we say welcome to the program.
that will make your understanding in physics much easier and enthusiastic. This is
The Newtonian notion.
To kickstart our physics discussion, Mr. Reian Mapue and Mr. Andrei Corcuera will be discussing about what is impulse and momentum. So, Reian and Andrei, take it away.
Thank you, Jamie. Hello, my name is Andrei Ramos Corcuera, and now let us have a deeper understanding about what is momentum and its connection to Newton's second law of motion. Momentum refers to the quantity of motion that an object has. It can also be defined as mass in motion. It is a vector quantity. It is given with the symbol lowercase p and has an SI unit of kilogram meter per second squared. As we all know, all objects have their own mass. So if an object is moving, then it has momentum. It has its mass in motion. There are dependent variables that can greatly affect the momentum of a certain object. These are the mass, which is the fundamental quantity of amount of matter with an SI unit of kilograms, and velocity, which is a derived quantity of the distance covered by an object in unit time, with an SI unit of meter per second. Therefore, we can define momentum as a product of mass and velocity, or simply the formula momentum is equals to mass multiplied by the velocity. The importance of momentum was recognized early in the development of classical physics. Momentum was deemed so important that it was called the quantity of motion. Newton actually stated his second law of motion in terms of momentum. The net or resultant force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. It is expressed in the formula net force is equals to change in momentum over change in time. And now that we know about the concept of momentum, let us now head over to Mr. Reian Mapue to tell us more about impulse.
Thank you, Andrei. Hello, my name is Mr. Reian Mapue, and let us now talk about impulse and the conversation of momentum. Impulse is defined as the term that quantifies the overall effect of a force acting over time. It is a vector quantity with the given symbol J and is expressed in Newton seconds. It is the product of the net force acting on an object and the time the net force acts on the object. In short, it is followed by the formula J equals force multiplied by change in time. This equivalence is known as the impulse momentum theorem that gives a direct connection between how a force acts on an object over time and motion of the object. One of the most powerful laws in physics is the law of momentum conservation. The law of momentum conservation can be stated as follows. For a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the objects after the collision. That is, the momentum lost by object 1 is equal to the momentum gained by object 2. Lastly, elastic and elastic collisions. In an elastic collision, the objects separate after impact and don't lose any of their kinetic energy. Meanwhile, an inelastic collision is one in which objects stick together after impact, and kinetic energy is not conserved. This lack of conservation means that the forces between colliding objects may convert kinetic energy to other forms of energy, such as potential energy or thermal energy. And that is it. Those are the discussions about momentum, impulse, conservation of momentum, and the elastic and elastic collisions. Let us now head back to our host, Charles, Jamie.
Thank you, Reian and Andrei, for that wonderfully taught educational discussion. Now that we all know about the concepts of momentum, impulse, as well as the conservation of momentum and elastic and inelastic collision, let us now take a closer perspective on its application in the real world through a physics laboratory experiment.
But before we proceed to the main experimental proper, let us have a closer look about the objectives of the experiment. First, to define momentum, identify the equation relating momentum to mass and velocity, identify the units of momentum, and identify the direction of the momentum vector. Second, to define impulse and describe its effect upon an object's momentum. Third, to use the impulse momentum change equation to analyze a collision in order to determine an unknown quantity in a collision problem. Fourth, to use the impulse momentum change equation as a guide to thinking about how a change in one quantity affects another quantity. And lastly, to explain a variety of applications of the impulse momentum change equation that pertain to safety. Now that we know about the main objectives of the experiment, let us now proceed to the experimental proper, which will be discussed by Mr. CJ Canlas. So, CJ?
Thank you, Charles. Good day to everyone. My name is Mr. Charles Josette Canlas, and I will show to you the materials and procedures for the laboratory experiment.
First, 3 different balls. In this experiment, we are going to use a ping pong ball, a baseball, and a tennis ball. Second, 3 different surfaces. In this experiment, we are going to use a tiled floor, a carpeted floor, and a cinder block, or you may use a concrete floor as a substitute. Third, a kilogram or a gram scale. Lastly, a meter stick.
Now that we are done in the materials for the experiment, let us now proceed to the primary procedures of the experiment.
First step, gather all the materials. Second, determine the mass in kilograms of each ball and record it on the datasheet. Third, drop each ball from a distance of 1 meter onto the surface and record how high it bounced in meters. Take note that you can have as many trials each combination of ball and surface to have more accurate results for the bounce height. In this experiment, we used 3 trials for each combination, granting an overall total of 27 trials. Fourth, note whether the ball and surface showed more of an elastic or inelastic collision. If the ball bounces up more than 0.5 meters, then it is more elastic. If it bounces up less than 0.5 meters, then it is more inelastic. Fifth, repeat steps 3 and 4 for the 2 other surfaces. Sixth, Calculate the velocity for each ball right before it bounces and right after it bounces. 7. Calculate the momentum for each ball right before it bounces and right after. 8. Calculate the percentage of momentum loss for each case. We are now going to show you a short documentation of our group's laboratory experiment.
So now we know about the step-by-step procedure as well as the execution of our experiment. We will now display to you the results as well as answering questions related to the experiment. As you can see in the table, we did 3 trials for each combination of ball and surface in order to produce the most accurate results. The baseball weighed 0.147 kilograms during the preparation of materials, which was the heaviest ball among the 3. After being bounced in a carpeted floor, it has an average bounce height of 0.35 meters, in a tiled floor 0.32 meters, and in a concrete floor 0.31 meters, all of which had a more inelastic collision, since the experimental values are all less than 0.5 meters. Same application goes to cases 4 to 6, which is for the tennis ball. It weighed 0.078 kilograms during the preparation, which was the second heaviest ball among the 3. Once again, 3 trials were made for each case. After being bounced in a carpeted floor, the tennis ball had an average bounce height of 0.45 meters, in a tile floor 0.467 meters, and in a concrete floor 0.427 meters, all of which had a more inelastic collision since the experimental values are all less than 0.5 meters. For ping pong cases 7 to 9, the ping pong ball weighs 2 grams or 0.02 kilograms, which was the lightest ball among the 3. Once again, 3 trials were made to produce the best results. The ping pong ball that was bounced in a carpeted floor had an average bounce height of 0.19 meters, which is a more inelastic collision. However, when the ping pong ball was bounced in a tile floor and in a concrete floor, it recorded an average bounce height of 0.568 meters and 0.517 meters respectively. The latter 2 ball surface combinations had a more elastic collision since they had experimental values greater than 0.5 meters.
Question number 2. Calculate the velocity of each ball right before it hits the surface. Why do you only have to perform this calculation once? To calculate the initial velocity, we will be using one of the kinematics equation, which is the derivation of the initial velocity from this equation to this. We used this formula because the initial height and the acceleration due to gravity are the only given, and the initial velocity are the following. You just need to calculate it once since all of the balls used in the experiment have the same height as their starting point, which is 1 meter above the ground, and it was performed in the same planet. Judging by the formula, only the acceleration due to gravity acts to the balls when it free falls other than its height. Question number 3. Calculate the velocity of each ball right after it hits the surface. The same thing goes for the final velocity, but this time, there's no need to derive the formula. We just need to substitute the values of the height of the bounce of the balls and the gravitational acceleration. Here's the result for the ending velocity.
In question number 4, we need to calculate the momentum of each ball before it hits the surface. The formula to be used must be starting momentum equals the mass times velocity. We must get the product of the mass of each ball and the starting velocity in order to find the starting momentum. On the first three cases of the baseball to carpet, tiles, and concrete floor, their starting momentum are all negative 0.65. And for the next three cases of the tennis ball to carpet, tiles, and concrete floor, their starting momentum are all negative 0.35. For the last three cases of ping pong ball to carpet, tiles, and concrete floor, their starting momentum are all negative 0.00886. As we can observe, each three cases of the balls in starting momentum are similar because at this point, the starting velocity is constant with a negative 4.43 meter per second. In question number 5, we need to calculate the momentum of each ball after it hits the surface. The formula to be used must be ending momentum is equals to mass times final velocity. We must get the product of the mass of each ball and the final velocity in order to find the ending momentum. For the first three cases of the baseball to carpet, tiles, and concrete floor, the ending momentum are negative 0.39, negative 0.37, and negative 0.36 respectively. For the cases of tennis ball to carpet, tiles, and concrete floor, the ending momentum are negative 0.23, negative 0.24, and negative 0.23 respectively. And for the cases of ping pong ball to carpet, tiles, and concrete floor, the ending momentum are negative 0.00386, negative 0.00668, and negative 0.00636 respectively. In calculating the starting and ending momentum, we should not forget the unit, which is the kilogram meter per second.
In calculating the change in momentum, we must need to subtract the ending momentum to the starting momentum. Then, once that it is computed, we can now proceed to calculating the percentage of momentum loss, which is the quotient of the change in momentum to the starting momentum, then multiply by 100. The quotient is expected to have no units since we are dealing about percentages only. The formula in changing momentum is final momentum minus initial momentum. In case 1, the given is the final momentum is negative 0.39 minus negative 0.65, which is initial momentum. The change in momentum is 0.26 kilogram meter per second. Then the percentages of momentum loss. The formula is change in momentum over initial momentum. The given here is, in case 1 is 0.26 over negative 0.65 times 100. The final answer or the percentage of momentum loss is negative 40.
Question number 7. Why did all of the balls lose momentum? What happened to the momentum that was lost? The balls involved in the experiment lost momentum when they bounced to different surfaces because their bounce heights are not equal or greater than 1 meter. In order for the balls to not lose momentum, they must attain a perfectly elastic collision, which is impossible in the real world. Thus, whenever a ball bounces here on Earth, its momentum decreases due to the fact that the kinetic energy of the ball is being transferred as heat, noise, or any related energy. Question number 8. What would happen if the collisions were perfectly elastic? If the collisions from the experiment were perfectly elastic, then the ball should have bounced back at a height of equal or greater than 1 meter. A perfectly elastic collision is only present if there is no loss in the kinetic energy of a certain object in the collision. In a perfectly elastic collision, the balls would follow a pattern of bouncing consistently without slowing down, unlike in the experiment, which is the usual pattern of decreasing bounce height as the ball bounces multiple times.
Based on your experiments, which ball would be best to use for dodgeball? For bowling, why? Based on the results of our experiment, the tennis ball is the best option for playing dodgeball. The tennis ball weighs more than the ping pong ball but weighs less than the baseball. The tennis ball, having more mass compared to the ping pong ball, could let players accurately throw the ball to hit opponents since it would be less likely to be affected by the wind. If the baseball was used, it could result in players getting easily tired since they would be applying greater force. On the other hand, the baseball would be the best option for playing bowling. The mass of the baseball would be fair enough for it to knock down the bowling pins. The throw or spin would be more accurate since it would not bounce around like the other option. Which ball and surface from the experiment would be best for playing basketball? What about street hockey? Why? The result concludes that the ball and surface that would be best for playing basketball is the tennis ball and the cemented floor. Even though the combination of tiles and ping pong ball has the highest bounce height, it would not recreate the feeling of playing and dribbling a basketball. The baseball was not a part of our option since it has the lowest bounce height. In addition, the tennis ball is also commonly used for dribbling drills in basketball trainings in order for a player to have a better grip on the basketball. On the other hand, the best option for playing street hockey would be the baseball and the cemented floor. The weight of a standard street puck is 0.130408 kilograms, and since the mass of the baseball is closer to the puck's, despite the shape difference, you would be able to apply the same force as you would in a typical puck and have an accurate shot. Lastly, since the other balls would bounce more, hitting them would result in an inaccurate strike.
All sports associations have hired you to develop the next big sport. They want you, as an engineer, to develop a sport that includes components of other sports. Describe your sport, including what type of ball and surface will be used and why.
We, the Newtonian Notion, made the proposal for the formation of a new ball sport made from existing ball sports. This sport is called concrete baseball golf.
It is a blended kind of sport where the mechanics of the sport of golf is implemented, but the major differences are the type of ball being used, which is a typical baseball rather than the usual golf ball, and the type of surface being used is a concrete floor, rather than the usual grass turfs. Baseball was selected as the official ball for the new sport since both baseball and golf ball have some certain similarities when it comes to effectivity, elasticity, and comfort.
According to an analysis made by Exploratorium's official website, or as seen in this picture shown in the video, the average bounce height percentage of a baseball drop at a certain height bounces back at around 32% of the height, while the golf ball accounts for 36%. Based from the figure alone, it could be interpreted that the baseball could be an effective selection for the concrete baseball golf, since the bounce height percentages are almost identical. Thus, the hitting of the ball could be the same as the usual golf.
In addition, from the experiment of our group, baseball has the least average bounce height among the tennis ball and ping pong ball being bounced in a concrete floor, making it the first ball to stop after multiple bounces. As we all know, placements are important in golf as it aims to have few attempts to win a game. So balls with lower bounce heights make the placement of the ball much easier and faster to determine.
Although the diameter of a standard Major League Baseball or MLB baseball, which is 73 to 75 millimeters, is larger than the diameter of a standard United States Golf Association or USGA golf ball, which is 42.67 millimeters. The baseball's composition played a significant role on its elasticity and loss in momentum. The cowhide shell, which is located at the exterior part of the ball, the yarn or the wool and cotton windings, which are located at the midpoint, and the round cushion cork peel in its core, could be the reason behind the similar average bounce height percentage of a baseball and a golf ball.
The official court of the concrete baseball golf should be almost or equal to the dimension of a standard soccer field, which is 125 meter by 85 meter with a solitary hole right at the other end.
In this particular experiment, we learned about the importance of the conservation of energy and momentum, that energy is never created nor destroyed, it only transfers or transforms to a different type into the environment. Based from the experiment, bouncing a ball at a certain height means that its return bounce is not the same as before, and it continues to decrease until it stops or slows down. Here on Earth, it is impossible to have a perfectly elastic collision, simply because of the law of conservation of energy. Developing a new ball sport from already established ball sports is a quite difficult task to think about it. The concrete baseball golf should not be too identical as the regular golf, for it to attract interest and to initiate a way of executing the sport. In addition, the selection or maybe creation of balls and surfaces greatly requires additional researches and engineering in order for the sport to be effective and enjoyable as much as possible. Wrong compatibility of the ball and surface could lead to wearing and tearing, difficult execution of plays, and others. Thus, the reason why certain balls have a standard pascals per square inch or standard weight to it. If it exceeds or lowers, it will greatly affect the overall performance of the sport, like its elasticity.
Due to the COVID-19 pandemic, it was hard to conduct an experiment as a group since we are in a new learning system. But then, we need to work in a more convenient way. Upon answering the questions from 2 to 6, which is the computations from the table 2, we had a little misconception which consumed a lot of our time. We have tried several computations before we've come up to a correct solution, which our instructor gave the appropriate formula needed to arrive with the starting, ending velocity and momentum. Hence, the objective of the experiment were notably accomplished. As we go through an in-depth exploration, our critical and analytical thinking skill expand over time.
We can conclude from the activity the effects of different balls from the different surfaces. We can also apply the results of our data to the different scenarios given in the questions.
To sum it up, I realized that they are not the same numbers exactly, even if they are all same weight, same height, or etc. In the end, they have different total numbers even if it's millisecond. They are different, and that's how important every single detail in recording the numbers. I also simply learned how to edit just simple editing in the video, but I am proud because I can do it until now when I try it. I learned also that every surface when the ball has been hit is with the same bounce or the same height as the other one. It depends on the type of the surface that the ball will hit and how high you will let go the ball.
Filtering the context of my conclusion, one thing totally etched in my mind: adjustments. It is very important when doing calculations, measurements, and experiments like this laboratory number 4, because real-life scenario is different from a physics system. Aside from being prepared and having knowledge, being able to adapt to the condition of the situation when doing physics experiment is a great feat of growth as future civil engineers.
And that is it, the experiment that accurately proves the concept of momentum and impulse.
We hope that this video will serve you as a beneficial knowledge to understand these concepts in a much easier and enthusiastic manner.
Once again, we are your hosts for today. My name is Gabriel Mijares,
And my name is Miss Jamie Ann Capili.
and we just want to leave a quote made from Sir Isaac Newton himself. What we know is a drop, but what we don't know is an ocean.
Thank you for watching this video presentation. Once again, this is
The Newtonian notion.